Hi, everybody. I wanted to show you how to do log transformations and specifications and econometrics in R. So we're going to work through an R script and see what we can get. So we'll first load the package tidyverse. We'll create a vector of years of education. So we'll have 1,000 observations. So we're just randomly picking numbers from 10 to 25 for 1,000 observations. Obviously, if we have 1,000, we need to have replacement. So there'll be people with 11, with 14, with 22, with 25, with 10. Then we're going to create earnings. So we'll have earnings vary nonlinear with education. So if we do it like this, and now we can gather those two in a data frame and plot them. And what we see is we have kind of it's hard to see here because we don't have that much variation in the X. Let's make the return be higher. So we'll make it be 6% return per year. So I'll sample again. I'll create the earnings. I'll gather them together in the data frame and the plot. And now we have sort of a more of a nonlinear function here. It's a little bit more curved. Um, we can make it really curved, right? If we go like 16 and then we'll create the data frame and then the ggplot and now we have it really curved. But 16% per year return to education will be phenomenal. So let's keep it at 3%, I think is fine. It should be illustrate. Now, you notice that when we simulated it there, everything's on a straight line basically, or on a curve. So we want to add some noise, right? We want to add some error, other factors, measurement error. So we're going to just randomly draw from the normal distribution 1,000 values and add them to each one of our observations of earnings and education. And our error will be mean 10 and standard deviation 10. So just as likely to be above as below the error. So it'll follow the classical assumption that the error is going to be just as likely to be some value above the predicted line as below the predicted line. So let's run that. So we'll have earnings and then our data frame. And now if we plot it, we see this looks like more what data that we see, right? Which is integers for years of education, and then a whole bunch of people with different earnings at every level of education. But the earnings are, of course, bounded. We don't see people earning. Let's imagine these are thousands of dollars a year. So these are annual salaries for our population. And we can eyeball this, right? Pretty clear that there's a positive relationship. Higher earnings means higher years of education, higher earnings. Here it looks pretty linear, right? But we know from our earlier analysis, this is actually a nonlinear relationship. So we might think, oh, in this general sense, we should apply the Mincer equation, the log linear transformation. So let's create um, in the data frame, we'll use the piping syntax. So we assign back to the same data frame. We use the pipe, and then we use the mutate command, and we say log earnings is equal to the log of earnings. So that's our new variable will be called log earnings, and it's just the transformation of earnings, transforming it to the log function. Now we can run some regression. So we'll call R1 we'll write as the linear model, and our data is equal to, we call it DF, and our model is earnings is a function of education. And we can do variations in that. Let's have earnings be a function of the log of education. So, log earnings. We can also calculate the log of education here. So we'll do log education, and we'll have education inside there, log of years of education. And now we can have the other specification. R3 will be log earnings and log of education. So three specifications, right? And since we have random noise here, we should expect pretty decent R squares for these. How do we gather these regressions together? First, let's make sure they all work. So we'll run them as a block, and didn't work because I did something wrong here, but it's earnings, right? Earnings. Yeah, so one education it's years of education. I really messed up here. Years of education, right? Syntax errors, right? So one, two, log earnings. It's log of earnings. Got them all wrong. Um, and this is called that. Maybe I didn't run this. There we go. Now I ran it. Yep. So we got R1, R2, and R3. We want to display them. We gather them together in the list. So we'll type list R1, R2, R3. And then we use model summary. And we'll display the lists of the three models that we have. And so we could actually give these names. So the first one is the linear, and the second one is the log linear. We forgot to do linear log, but that's okay. We'll just do two of them. And then the third one is log log. So that now they have names when they appear for the columns, right? So we'll do model summary. We want to have stars equals true to give us the asterisks for the significance tests. And we'll have goodness of fit be it's equals C of the standard error of the regression, root mean squared error, uh, the number of observations, and let's have the R square. I think it's R squared. I don't know the exact syntax there. Okay, so we got everything here. Yep. So we gather them together and we display. We didn't load model summary here, so I need to load up the package. Package is loaded, and now we can run the command and get our table. And there's our regression results, three regressions. The linear one it tells us that each year of education is associated with a 2.62 dollar, whatever the units of log earnings were. Maybe they were in thousands of dollars, so it'd be a 2,000, $2,600 increase. Our log linear tells us each additional year of education is associated with a 2.8% increase. We multiplied by 100, right? So it's a 2.8% increase in earnings. And right, that's pretty close to our 3.03. So we recover that. That's good. And then our log specification tells us that a 1% increase in education is associated with a 0.46% increase in earnings. The elasticity of earnings with respect to education. A 1% increase in education is associated with a 0.46, say 0.5% increase in earnings. So those are our three specifications and our three interpretations. So we didn't do the linear log, which doesn't have much meaning in this case. Would be like, oh, how much increase in earnings for a 1% increase in education, which isn't a question, and no one would ever frame it that way in that sense. So I hope you found this useful. And again, you can easily copy this script in R and practice it yourself with different numbers and different coefficients here. This 0.03 is sort of like, right, what the growth rate is of earnings with education. So change those numbers, see if the regression works. You can change the R square here. I didn't write it. Oh, I wrote R squares. So it should be R squared. Now we'll get what is our R squared? 0.58, right? So if we made the noise bigger, so if we made this be 20 and we run the whole thing again, I'll just highlight it and run it all again, R squared go down, right? So we see adding more noise to it makes the R squared go down because now there's more variation, random variation, measurement error, other factors, random stuff determining people's earnings and education. So the R squared goes down. Hope you enjoyed this video. Look forward to talking more about log specifications in class.